Welcome to a screencast on acid equilibria and calculations. The objectives of this screencast are to use acid ionization constants to assess the relative strengths of acids, also related properties such as pH and extent of reaction, and to carry out equilibrium calculations for weak acid systems, which would include determining equilibrium constant values, pH and pOH, as well as concentrations of equilibrium species and percent dissociation. To start, let's consider the weak acid nitrous acid, HNO2, at 25 degrees Celsius. And HNO2, when it dissolves in water, dissociates. It dissociates partially. The H from the HNO2 adds to the H2O to make hydronium ion H3O+, and then the nitrite ion NO2- separates. And this is an equilibrium, and it's a partial dissociation. And the equilibrium constant for this expression, that is, for this reaction, is K sub A, where A stands for acid dissociation constant, is H3O+ concentration times NO2- concentration over HNO2. And the H2O liquid is not included in the equilibrium constant expression, even though it is not it's not pure. It has an effectively pretty constant concentration, and so by convention we don't write that in here. And as noted, this is called an acid dissociation constant. Okay, so how do we determine these? Well, we can measure the pH of an acidic solution and then use that and what we know about equilibrium to determine K sub A values. So a 0.20 molar nitrous acid solution is found to have a pH of 2.03. It was measured experimentally, and we'd like to determine the K sub A value for HNO2. Well, the reaction is this. HNO2 reacts with H2O to make H3O+ and NO2-. And if we do our usual ice table, our initial concentrations, and just note that the initial here is in quotations because it's kind of like a fake initial. What we do here is we pretend that this solution has not dissociated. So we use its nominal concentration. We took 0.20 moles of HNO2, dissolved it in a liter of solution, and when that is formed, it makes the solution, but it also dissociates right away, but we pretend it doesn't. So we say 0 and 0 for H3O+ and NO2- concentrations, and this is just for purposes of setting up the ice table and being able to do the calculations. This isn't what really happens. All this happens all at once, I should say. So if this is the case, if we pretend there has been no dissociation, then of course some dissociation has to occur to reach equilibrium. So the HNO2 concentration goes down a bit, the H3O+ and NO2- go up a bit. We're not worrying about H2O because it has an effectively constant concentration and it's not in our equilibrium constant expression. So at equilibrium, we have 0.20 molar minus X for the HNO2 concentration, and X and X for the H3O+ and NO2- concentrations, respectively. Okay, now we're trying to find the K sub A value, and as we just saw earlier, the K sub A value is this, or the K sub A expression is this ratio of H3O+ times NO2- concentrations divided by the HNO2 concentration. So if we can figure out the equilibrium concentrations of each of these substances, we plug them into here and we're good to go. Well, how we get this is by using the pH value. And as seen previously, we know that pH is related to H3O+ concentration by pH equals negative log of H3O+ concentration. Therefore, H3O+ concentration is 10 to the minus pH. And if we plug in 10 to the minus our actual measured pH 2.03, that gives us 0.0093 molar for our H3O+ concentration. And note, that is this value. So at equilibrium, we know that both the H3O+ and the NO2- concentrations are 0.0093, and then that value can be subtracted from the 0.20 molar nominal nitrous acid concentration, and what we get at equilibrium is 0.0093, 0.0093, and 0.19 for our concentrations of the three species involved in the equilibrium constant expression. And if we plug them into our equation, we calculate a K sub A value of 4.5 times 10 to the minus fourth. Notice this is a pretty small value, indicating a small dissociation or small percent dissociation that the HNO2 undergoes. And this process can be used to determine the K sub A value for any acid. Measure the pH, use what we know about equilibrium to calculate K sub A value. Now, these acid dissociation constants for different acids can be found in tables. This is a small table showing just a few acids. It includes hydrobromic acid, which is a strong acid, almost fully dissociates. It has a really, really big K sub A value. Nitrous acid we just did, and then acetic acid, hypochlorous acid, and hydrocyanic. And you can see the range of K sub A values, and the smaller the K sub A, the less the acid dissociates, the more reactant favored it is. Larger the K sub A, the more the acid dissociates, and the stronger the acid is. And we sometimes use something called pKa, where, like with pH and pOH, P means negative log of, so pKa is negative log of Ka, and if we take the negative log of 10 to the 9th, we get about -9. So remember, logarithms are like exponents, so the pKa of hydrobromic acid is -9. We do the same thing to nitrous, acetic, hypochlorous, and hydrocyanic and get the pKa values that are shown. And note that a large K sub A corresponds to a more negative, if you will, pKa, or a smaller pKa, if you want to look at it that way on the number line, and a very small K sub A corresponds to a larger pKa, and stronger acids are at the top of the table if it's organized this way, and weaker acids are at the bottom. Okay, in general, an acid HA, we often just use this as a generic form, H something. So the generic acid HA partially dissociates like this. The H and the A split apart. The H plus attaches to H2O to make hydronium ion, and then the A minus, the conjugate base, is separated from that. The K sub A expression is the usual form, H3O plus times A minus over HA concentrations. And we can now use this. If we have Ka values, we can determine pH of solutions without actually measuring. So usual equilibrium stuff now applied to acids. What is the pH of a 0.20 molar HClO solution? And the reaction is HClO reacts with water to make H3O plus ClO minus. Our initial is 0.20 molar, and we pretend again it hasn't dissociated, so 0 and 0. We know it really has to dissociate, so negative x and minus x and plus x and plus x. And then at equilibrium, 0.2 minus x and x for the concentrations of the species that are of relevance here. And then K sub A, usual form, H3O plus times ClO minus over HClO concentrations. And that equals x squared over 0.2 minus x. And note, this time we don't know the pH, so we can't determine x in that manner. But if you remember on the previous table, we know what the K sub A value is for HClO. We can look it up, and it was 2.9 times 10 to the minus 8th. And so now, in the usual manner of previous equilibrium stuff, we now have an equation where we know the answer, so to speak. We know the K sub A value, but we don't know the x. So we can solve this. And if we solve, we get x equals 7.6 times 10 to the minus 5th. And since that x represents the H3O plus concentration, that means that the H3O plus concentration at equilibrium is 7.6 times 10 to the minus 5th molar. And since the question asks for the pH is the negative log of that. And so the negative log of 7.6 times 10 to the minus fifth is 4.12. So the pH of this solution is 4.12. Okay, one more question. What's the percent dissociation of this 0.2 molar HClO solution? And notice the dissociation, we start with nominally 0.20 molar, and when it dissociates, we make X, which we just figured out previously, for the amount of the HClO that is broken apart into H3O plus and ClO minus. So this is the amount that has dissociated compared to the starting amount of 0.2 molar. So in general, when we know that number now, it's 7.6 times 10 to the minus fifth molar. So the percent dissociation is how much is dissociated, 7.6 times 10 to the minus fifth molar, divided by the original concentration, 0.20 molar, times 100 makes it a percent. And if we do that calculation, it's 0.038% dissociated. And note, this is a very small percent dissociation, and hypochlorous acid was a pretty weak acid with a very small case of A value. So that is it for an introduction to acid equilibria and calculations.